Now the second test that we can depend on to arrive at C and phi, the shear strength parameters of soil, is a triaxial test. A triaxial test was designed considering the demerits of direct shear test, and the shear force is not applied directly. Instead, the compressive forces are applied, which induces the shear failure on an inclined plane. So while discussing the direct shear test, we mentioned that the shear failure happens along the predetermined failure plane, which means that we fix the failure plane, which is nothing but the plane that separates the top and the bottom box, and the soil is forced to fail along that surface. Plus, the second demerit was that you are directly applying the shear stress. Now these two demerits are solved in this triaxial test, where you do not apply the shear force directly. Instead, you apply the compressive force, which in turn induces shear failure on inclined planes, which is what actually happens in the field condition. Now you have two stages in triaxial test. The first one is a consolidation stage, and the second one is a shearing stage. To understand that, let's take the triaxial sample. Usually the triaxial sample of soil is a cylinder whose dimension in diameter is 38 millimeters and height is 76 millimeters. So that's 3.8 centimeter diameter and 7.6 centimeters height. So that's a soil sample that we have for triaxial test. Now the preparation of such a soil sample can be detailed taking one entire video, which is skipped for the time being because it's not involved in your syllabus. Now nonetheless, you have this triaxial soil sample which undergoes two stages, the consolidation stage and the shearing stage. In the consolidation stage, the specimen is subjected to an all-round confining stress or confining pressure, let's say sigma C. So you have the soil sample here, and under consolidation stage, water pressure is applied around the sample using the triaxial test setup. So water squeezes the sample, and the specimen, the soil specimen, is subjected to an all-round confining pressure from the water, which we denote as sigma C. The second stage is a shearing stage. So in the consolidation stage, there's an overall confining pressure applied onto the soil sample, and in the shearing stage, an additional axial stress, which is called as a deviator stress, sigma D, is applied on top, like this. So earlier you had an overall confining pressure, where the soil sample was subjected to water pressure throughout the circumference and also the top and the bottom, and in the shearing stage, an additional stress, sigma D, is applied on the top. So you have the soil sample here. Confining stress, sigma C, will be the minor stress which gets applied through the circumference and also on the top and the bottom, and the deviator stress, sigma D, is an additional stress. So sigma 1, the major principal stress, equal to sigma C plus sigma D, and the minor principal stress is sigma C itself. So you have the major principal plane, that's a circumferential plane. The minor principal plane, that's a circumferential plane, and the major principal plane, that's the top and the bottom. So the major principal plane has major principal stress, sigma 1, which is equal to sigma C plus sigma D, and the minor principal plane, which has a minor principal stress, sigma 3, which is equal to sigma C, the confining stress. And when you have a critical combination of sigma 3 and sigma 1, just like we discussed when we were discussing the Mohr-Coulomb circle, when you have such a critical combination, there will be a shear failure along this plane. Let's say there will be a theta angle with respect to the horizontal, and the failure plane will have its own component of sigma and tau. So sigma and tau will be functions of sigma 1 and sigma 3, and when it reaches a maximum shear stress it can take, the soil fails along this plane. That is a concept. So nowhere in this test you are applying direct shear. Instead, you are applying just the compressive loads, a combination of which induces failure along the surface. So the test setup looks like this. You have a triaxial cell which has a perspex chamber, a transparent one, inside which you can place a soil sample, and you have a loading mechanism where axial deviator stress can be applied on to the soil sample, and this chamber, when filled with water, gives the confining stress sigma c. So the confining pressure sigma c is a minor principal pressure or the stress, and sigma c plus sigma d is a major principal stress. So you have the zoomed in picture of this soil sample here. The soil sample is sandwiched between porous stones, and above the top porous stone you have a specimen cap which is attached to the mechanism which applies the deviator stress. So this soil sample is zoomed here, and the soil sample is kept within a membrane. So the membrane wraps the specimen, and above the membrane and below the membrane there are porous stones, and above this porous stone you have the specimen cap. So this is a soil sample in schematic which gets applied with sigma c or sigma 3, which is due to the water pressure when water fills into this chamber, and sigma 1 is a major principal stress which is equal to the water pressure plus the deviator stress that you apply from this load mechanism. So such a combination will give rise to failure. So when you increase sigma d using this mechanism, it will induce shear failure on the inclined plane EF, the inclined plane. So you can have different combinations of sigma 3 and sigma 1, and at some particular combination of sigma 3 and sigma 1 there will be failure along this plane. Now the types of test based on the drainage. One of the disadvantages of the direct shear test was that you didn't have option to control drainage, and you didn't have option to have pore pressure measurement, which again is an advantage here for triaxial test. Triaxial test typically has two different stages of test. The consolidation stage, where you apply the confining stress sigma 3, and the shearing stage, where you apply the deviator stress sigma d to get the sigma 1. Now based on the drainage condition, which means water is allowed to move in and out of the sample or not, the tests can be divided and classified into the following: UU test, unconsolidated, undrained; CU test, consolidated, undrained; and CD test, consolidated, drained. So the first thing that you should keep in mind is that you have the option to allow water to move out of the sample or not. So you have the option to measure the pore pressure or not. So for which the schematic here, and the cell pressure or the confining stress is applied through this inlet. So through this inlet water moves in, saturates the soil sample and fills the perspex chamber. And there's an option to have pore pressure and back pressure measurements here as outlet valves. So these mechanisms allow you to control the water movement out of the soil sample, based on which you can have UU test, CU test and CD test. Now UU test, unconsolidated, undrained, means that no drainage is permitted during consolidation stage and no drainage is permitted during shearing stage. So we have two stages, consolidation stage and shearing stage, and in neither of these stages you allow water to pass out. So which means that soil fails quickly, and it's called as Q test because it fails quickly. Second is consolidated undrained stage, in which drainage is allowed during consolidation stage, but drainage is not allowed during shearing stage. So consolidation, undrained. In consolidation stage, you allow drainage. In shearing stage, you do not allow drainage. It's called as R test. Third test is a consolidated drain test or CD test, where drainage is allowed during consolidation stage and drainage is allowed during shearing stage as well. Both of these stages take time and the water needs to escape out. So it's called as a slow test or an S test. So when you allow water to escape out, it means that the soil has to take longer time to fail. So it's called as a slow test. And here you have the quick test Q, here you have the slow test S test, and in the middle you have R test, for no other reason that R falls between Q and S in the alphabetical order. A few merits and the demerits of triaxial test are listed here. Merit number 1, the drainage conditions can be controlled. Merit number 2, the specimen is free to fail on its weakest plane, unlike the direct shear test. Third merit is that the stress distribution is uniform on the failure plane. But it has got its own demerits. The apparatus is elaborate and costly. The drainage takes longer time, and in real field condition, the soil conditions are 3-dimensional and not axisymmetric like this. Here you take an axisymmetric cylindrical sample, but in real field condition, you don't have such a sample of soil. Instead, what you have is a 3-dimensional soil volume. So these are few demerits and these are few merits of triaxial test. Irrespective of all these demerits, triaxial test is usually followed, at least in our country, to have dependable values of C and phi. The third test you can have in the laboratory to find the shear strength parameters is the unconfined compression test. Now, while we discuss the triaxial test in the laboratory, we said that you take a soil sample in cylindrical shape and its dimension is usually 38 mm in diameter and 76 mm in height, and you apply water pressure surrounding the soil and also the top and the bottom, and it is the minor principal stress or the confining stress. And once you apply the confining stress, its consolidation stage takes place, and in the shearing stage you apply the deviator or the axial stress, and the confining stress sigma 3 and the deviator stress plus confining stress sigma 1 will be the minor and the major principal stresses. So a combination of these minor and the major principal stresses will induce failure on an inclined plane theta with respect to horizontal, and tau will be the shear stress. So when you increase the critical combinations of sigma 3 and sigma 1 such that tau goes on increasing, and at some point the soil fails in shear. This was the story about the triaxial test. The difference in unconfined compression test is that you don't have the confining stress, which means you don't have water pressure confining the soil sample, and you don't have sigma 3, the minor principal stress. So confining stress is 0. Sigma c equal to sigma 3 is equal to 0, which means you don't have these arrows here and you don't have minor principal stress. And it is conducted on self-standing soil or clay soil because it needs cohesiveness to stand on its own when prepared to the shape of a cylinder. If you have sandy soil, it will not have the property to stand on its own. It will fail even before testing. So earlier your Morse circle was like this. You had sigma 3 and sigma 1, and S equal to C plus sigma tan phi was our Moore-Coulomb equation. So sigma 3 was a minor principal stress, but in this particular unconfined compression test you don't have sigma 3, so you'll have a new Morse circle like this where sigma 3 equal to 0 and you just have sigma 1. So S equal to C plus sigma tan phi we'll have C here, and C will be the cohesive intercept. When you draw a line, it will not have a slope, which means 5 will be equal to 0. So C, the radius of the motorcycle, will be equal to half the diameter. So C is the radius of the motorcycle and half the diameter, which means C equal to sigma 1 by 2 equal to QU by 2, the ultimate stress by 2. So for an axial load applied P on a soil sample with cross-sectional area A, QU equal to P by A. So when you apply P load here on an area, cross-sectional area of A, P by A will be the ultimate load QU at the failure. And QU by 2 will directly give you the cohesive strength C, based on and explained by this motorcycle. So the test setup looks like this. You have a reaction frame and a reaction beam here, and the soil sample is kept between two plates, and you have the mechanism here which moves this bottom plate upward and it squeezes the soil, or in short you are applying an axial load on the soil sample using this mechanism. So you have the soil sample here, and above which you have the top plate, and a dial gauge is attached to the top plate, and the dial gauge measures the deformation of the soil sample. Here you have what we call as a proving ring, which measures the load that is acted on the soil sample. So you have the load frame here, you have the reaction beam here, you have the proving ring here, you have the dial gauge here, and you have the soil sample here kept between the top and the bottom plates. As you can see in this picture, the soil is not confined. You don't have a chamber, you don't have water pressure. It is self-standing like this. The zoomed in picture is shown here. The soil sample is self-standing, which means it's not confined at all. Sigma 3 equal to sigma C equal to 0. The dial gauge is shown here and the proving ring is shown here. And when you operate the machine, the bottom plate moves up, which applies an axial load on the soil sample, and the deformation will be measured by the dial gauge, and the load will be measured by the proving ring. So at some point, as the test progresses, the soil may start to bulge out, or it may get sheared along an inclined plane. So that threshold load is measured from the proving ring, and it will give you the stress when divided by the cross-sectional area. So that stress will be QU, and half of QU will be the cohesive intercept or the cohesive strength of the soil. A few merits of the unconfined compression test is shown here. It is simple and quick. It is suitable for UU testing of soil sample, and it's suitable to determine the sensitivity of soil. A demerit is that it is misleading for soils with internal friction angle. This test is exclusively for cohesive soil, and if you have sandy soil content in it, it'll mislead the results, because the only result that you get from this test is the cohesive strength. Or if at all the soil has a shear strength due to the angle of internal friction, it will not be accounted for while you get the results. Also, it cannot be performed on fissured clays. The next test that you can resort to is a Vane shear test to arrive at the shear strength parameters, C to be specific. It is used to determine the undrained shear strength of clay, and Vane shear test can be done in the laboratory and also in the field, depending on the dimension of the vane that you use and also the machine test setup that you can practice. So the vertical steel rod with 4 steel vanes like this is used in the Vane shear test. You have a central steel rod and you have 4 vanes or blades attached to the central steel rod. It will have a diameter D and a height H a typical value being 38 mm and 76 mm. The lab test setup is shown here, and the field vane shear test setup is shown here. Of course, the dimensions are different, and the vanes in either of these test setups are lowered into the soil, and a torque is applied to the road, the central road, which is measured by an indicator. So you have a assembly to measure the torque that you apply onto the steel rod, and like this you apply this torque. So when you apply the torque onto the steel rod, the vane starts to rotate, forming a cylindrical circumferential failure plane in the soil. So when you use it in the field, you can lower this entire test setup using steel extension rods into the soil sample so that the vanes get immersed into the soil sample, and when you apply the torque, vanes rotate and it forms a cylindrical failure surface, quite similar to the laboratory test setup. The shear strength S is related to the torque T required to induce shear failure around the cylindrical surface. So in short, you measure the torque T and you get the shear strength S. For you to understand the relative size, I have a slide here. So if this is a laboratory test setup, the field test setup would look like this. So this is a relative size of these two test setups. Now, when the vane is completely immersed in clay, the relation between S shear strength and torque T is here, as equal to T by pi into d square h by 2 plus d cubed by 6, where d is the diameter and h is the height, T is the torque. And this is a case when you have the vane completely immersed in the clay. But when the vane is immersed only to a depth h1, S is equal to T by pi into d square h1 by 2 plus d cubed by 12. So when the vane is not completely immersed and only h1 depth is immersed into the soil, you use the second equation. And when the vane is completely immersed in the soil, you use the first equation. So from either of these equations, you will arrive at the shear strength of the soil. And to find the sensitivity of the soil, the vane is operated in the undisturbed sample first and then on the remolded sample. So you immerse the vane into the soil sample, rotate it, apply the torque and measure the torque value at failure, from which you will get the shear strength. Likewise, you remold the soil sample and conduct the same test on the remolded soil, and you'll get a different value for shear strength. And you take the ratio of the undisturbed shear strength to the remolded shear strength, and that will give you the sensitivity of the soil.